Okay, so chapter 3, we are talking about water and the importance of water in biology. Without water, there is no life. So this is of utmost importance to us as biologists to understand water and all of the features of water and how it supports life. What are the features of water that allow it to support life? So we're going to spend an entire chapter just talking about water. Okay, so water is the molecule that supports life. It is the biological medium on Earth, and living organisms require water more than any other substance. Most cells are surrounded by water, and cells themselves are made up of about 70 to 95% water. So inside your cells is water, mostly outside your cells is water. Water is the main reason that Earth is habitable. So if we think about a lot of the research that's going on now in planetary science and looking for life on other planets, really what they're looking for is water. And if they find water, then that tells them that that planet could sustain life. So we're going to talk more about that as we go through this chapter. Okay, so there are 4 characteristics of water that make it very special and allow it to sustain life. The first of that is the fact that it is polar. It's a polar molecule made up of polar covalent bonds. So if you remember back in chapter 2, we talked about polar covalent bonds. Water is what we call the universal solvent. There are lots of molecules that will dissolve in water, particularly ions and other polar substances. We refer to those substances as being hydrophilic or water-loving, and water also repels what we call hydrophobic substances or water-fearing substances. These are going to be your non-polar substances. We'll talk more about these 2 things in just a second, but the fact that water is this universal solvent makes it very useful for us as a delivery tool for drugs and other things that we need to get inside our bodies and inside our cells. Water has a very high cohesive property, and if you think about the word cohesion, it means sticking together or working together. And basically what we find is that water molecules stick to each other and they're very cohesive, and it's a really important property of water, particularly when we talk about plants. Water also has tremendous temperature stabilizing effects, meaning that it takes a lot of heat energy to raise the temperature of water, even 1 degree Celsius. If you think about this, it's important. Our cells are 70 to 95% water, and the outside of our cells is mostly surrounded by water. We wouldn't want a molecule inside our cells that is not resistant to temperature changes. When we go outside and it's a 100-degree day, if our water, the medium surrounding our cells were susceptible to changes in temperature very easily, that fluid might start to boil, and that would be bad for us. So we really want a substance inside our cells that is going to be resistant to temperature changes, and water does that for us. So let's talk a little bit about this polarity feature of water. So we know that water is H2O, so it's 1 hydrogen molecule and 2 oxygen molecules. And remember, if we think back to chapter 2 when we talked about polar covalent bonds, we're talking about these bonds right here. We have electron sharing happening because that's what happens in polar or in covalent bonds. And remember, with polar bonds, that means that there's unequal sharing. And so what happens here is oxygen is very electronegative, and so the electrons spend a lot of time around oxygen, which gives it this sort of partial negative charge. Hydrogen is less electronegative, so the electrons spend less time around hydrogen, which gives it a partial positive charge. Basically, oxygen is pulling on these electrons more so than the hydrogen, and that's what makes this a polar bond. The polarity of water allows water molecules to form these hydrogen bonds with each other. So for example, if we had another water molecule over here, this guy would have their partial negatives down here with the oxygens, and this hydrogen would have a partial positive. So we would have an attraction between the partial positive hydrogen of one water molecule and the partial negative oxygen of another water molecule. So this dotted line here represents our hydrogen bond. And we talked about hydrogen bonds in chapter 2 and how they were a special type of bond that's important to us in biology. When we use the term hydrophilic, we are referring to water-loving. It really means water-loving. And these are other polar molecules that dissolve in water because it's polar. So anything that is polar will likely dissolve in water due to the polar nature of these bonds. Anything that is hydrophobic or water-fearing will not dissolve in water because water's polar. It's not nonpolar like them. So the key here is like dissolves like. That means polar things dissolve in polar solvents and nonpolar things dissolve in nonpolar solvents. Okay, so this is just a much better picture of what I tried to draw for you on the previous slide. So this is, it's messed up a little bit here, but these are our hydrogen bonds. This picture is representing hydrogen bonds. So here we have 5 water molecules, so I'll just number them, 1, 2, 3, 4, and 5. Our oxygen molecules are the big red balls, and our hydrogen molecules are the little silver balls. So you can see, again, remember that these hydrogens would have these partial positive charges, and the oxygens would have the partial negative charges. So what happens here is this partially positive hydrogen is attracted to this partial negative oxygen up here. Same thing over here, for example. We have a positive hydrogen here. This is going to be attracted to this partial negative oxygen. And so these little dotted lines in between the water molecules, those are our hydrogen bonds, and that's what gives water a lot of its unique properties, particularly that cohesion and the temperature stabilizing effects. Okay, so let's talk a little bit about that feature of water that makes it a universal solvent. So remember we talked about the fact that like dissolves like. So polar solvents dissolve in water or other polar solutes. Nonpolar solvents will not dissolve in water or H2O. So water will dissolve other polar molecules or ions. So ions also will dissolve in water, and that's what this is an example of, or a picture of. So here we have NaCl. If you remember back from chapter 2, we talked a little bit about how NaCl forms. That's sodium chloride, and this is table salt. So when you take table salt and you put it in water, what does it do? What does it do? Well, we all know that it dissolves, and it dissolves because it breaks apart into its ions. So table salt is made of positively charged sodium ions and negatively charged chlorine ions. So remember, water has charges too. It's got the partially charged positives and the partially positive hydrogens and the partial negative oxygens. So what happens is we have electrostatic interactions that happen here. All of our negatively charged oxygens are going to interact with or turn towards our positively charged sodium. On the flip side of that, our positively charged hydrogens are going to turn to and interact with our negatively charged chlorine. This is what allows salt, sodium chloride, to dissolve in water. It breaks apart into these ions, and we get these favorable electrostatic interactions. Okay, so let's talk about these temperature stabilizing effects. So we know that water absorbs heat energy before it gets hotter. So for example, you have a pot of water that you put on the stove, you turn the burner on, does it boil immediately, right away, as soon as that burner gets hot? The answer is no. It takes a while for that water to boil. It has to sit there on that hot burner for a while before that water is going to boil and get measurably hotter. That's because during that time, the water is absorbing the heat energy from the stove, from that burner, and it's taking it in, and it's going to serve as what we call a heat reservoir. It's holding the water, it's holding the heat in. The water is holding the heat in, and the temperature is going to remain stable for some time. If you were to put a thermometer in that pot of water, you would see that for a little while that temperature is going to remain stable. It's going to take some time before that water starts to get measurably hotter. So here's why that happens. What happens is, as substances get hotter, as the temperature starts to rise in that water, the molecules are going to start to rub together. So remember, they are connected through these hydrogen bonds. Okay, so all these dotted lines here that I'm circling in yellow, those are your hydrogen bonds. So the molecules can rub together through those hydrogen bonds, and what has to happen, so as those molecules start to rub together and as the temperature gets hotter, those hydrogen bonds have to break in order for that to happen. Okay, so that's where all these little X's come in here. Those are your hydrogen bonds breaking. So in order to allow these water molecules to rub together and create that friction that's going to increase the temperature, we have to break those hydrogen bonds, and that requires a lot of heat energy. So breaking hydrogen bonds requires a lot of heat energy. So we said back in chapter 2 that they were weak interactions, but remember we said they were strength in numbers. So when you have water, your pot of water on the stove, you've got all these hydrogen bonds holding those water molecules together. It's going to take a lot of heat energy to break all those hydrogen bonds that would then allow these water molecules to rub together and let that temperature of the water start to rise. That's why it takes a few minutes for that water to boil when you put it on the stove. This is so important for our cells. So this stabilizes the temperature of our cells, which, as we know, are filled with water, so that when we go outside on a 100-degree day, our water in our cells is not going to boil. If that were to happen, we'd be in big trouble. All right, so let's talk about these cohesive properties then. Remember we said that, again, these water molecules are held together with the hydrogen bonds, and it's because of those opposite charges, the partial negative charges on the oxygens and the partial positive charges on the hydrogen are creating these hydrogen bonds that are holding the water molecules together, creating this sort of attraction between the water molecules. This is really important, like I said, for plants. So what we know is that as water evaporates, so you can see here, I'm circling in yellow, we have water molecules that are leaving our leaves due to evaporation. Okay, so we can think that we might have a bright sunny day up here. Here's our sunshine. It's a hot day, and that's going to cause evaporation, cause water to leave the cells within the leaf of our plant. Well, we can't just have that water evaporate and not replace it, not if we want to have a healthy plant. So any water molecules that evaporate or that leave the plant due to evaporation have to be replaced. And where does that water, where's that replacement water going to come from? Well, it's going to come down here from the root system, which I've circled in yellow. So here's our root system down here. That is always going to be pulling in new water molecules from the ground, from the soil. So it's sort of like, you can sort of think of it, and I'm going to draw them as little yellow dots, but you can sort of think of this as a train of water molecules all the way down the stem of that plant. And as we pull on these water molecules from the leaves, and as they leave the plant, we pull all of these water molecules up to replace the ones that have left. So if you think about a train, right, this is going to be a really bad train, but here's my train. If I were to pull on car number 1 of my train and I grab it and I pull it in that direction, cars 2 and 3 are going to follow, right? And that's exactly what happens with these water molecules. When we pull on the ones up here and the leaves and they get pulled out due to evaporation, the water molecules from the roots, because they are all stuck together, follow behind. And that's the key here. So the key to our train being pulled are these linkages between our cars. If this link is broken, if we pull on car number 1, 2 and 3 aren't going to move. But if that link is there, okay, so if that link is there and we have a strong connection, like we do with the hydrogen bonding in water molecules, we pull on car number 1, 2 and 3 are going to follow. All right, so let's talk a little bit about acids and bases. This is really important properties. When we think about water, we have to think about how substances interact with water. So when we think about acids and bases, we're talking about these in terms of hydrogen ions and hydroxide ions. So our hydrogen ion is a hydrogen atom that has lost an electron. So we know that hydrogen, if you go back to chapter number 2, hydrogen has 1 proton and 1 electron. So a hydrogen ion is an atom that has lost that electron. So it is basically a proton. Okay, so that's basically what we're talking about when we think about a hydrogen ion. A hydroxide ion, so that the symbol for that is OH negative. So that is an oxygen atom, a hydrogen atom, and an extra electron. So if we think about water, right, we could take that hydrogen ion, we could take that hydroxide ion, and we put those things together to get water. Notice I drew both the forward reaction here and the backwards reaction. So we can take hydrogen ions and hydroxide ions, put them together to make water, or we can break down water into hydrogen ions and hydroxide ions. Okay, so if we think about pure water for a second, this is not water from your tap. We're talking very pure, double distilled water. It has both of these forms in it. So we have our H2Os, those are our typical water molecules that we think about, but we also have our ions. We have our hydrogen ions and we have our hydroxide ions. The key when we think about pure water is that the number of hydrogen ions equals the number of hydroxide ions. So that is really key when we think about pure water. Yes, we have hydrogen ions and yes, we have hydroxide ions, but they are equal. The number of hydrogen ions equals the number of hydroxide ions. Okay, so let's talk about definitions of acids and bases. And then we'll talk about another substance that's going to be really important to us called buffers. So an acid is a molecule that releases hydrogen ions when it dissolves in water. So it donates free hydrogen ions. So I'll show you an example of this in a second. A base is a molecule that's going to remove free hydrogen ions when it dissolves in water. So it's going to combine with other free hydrogen ions to make water. And we're going to look at that in a second in a picture. Buffers are going to be really important for us in biology, and these are going to be molecules that stabilize the pH. So we'll talk about pH and what that means if you're not familiar with that term in just 1 second. But buffers can do either one of these things. They can release hydrogen ions like an acid, or they can remove hydrogen ions like a base. So buffers can function as either an acid or a base. All right, so let's refresh our memories on pH. Hopefully this is a term you've used before or remember from high school. pH is a measure of the amount of hydrogen ions in a substance. Okay, so we can look at lots of common substances that we use every day. For example, lemon juice has a pH of about 2. Tomatoes, a pH of about 4. If we think about milk that we drink, it's got a pH of about 6.6. There's our pure water at 7. So remember, our hydrogen ion concentration equals our hydroxide ion concentration. Very important for us in biology is that our blood is at a pH of about 7.4. For example, we can think about our oven cleaner, that's at a pH of 13. So anything above 7, so anything up here in this area, we refer to as an acid. Anything below 7, so any number below 7, 6, 5, 4, 3, 2, 1, we call that an acid. Anything above 7, so 8 to 14, we call that a base. Okay, so remember, these guys are going to release hydrogen ions. These guys are going to remove hydrogen ions. Okay, so let's take a look at how this would work. So we have our water. We have, remember, some water molecules. That's our H2Os. We're going to have some free hydrogen ions in there because that's what happens. Water has these hydrogen ions. What happens is when we add an acid to water, so we're going to add hydrochloric acid, that is going to donate hydrogen ions or release hydrogen ions to the water. So we end up with all these extra hydrogen ions in the solution that weren't there before. What happens is the more hydrogen ions we get released, the more acidic the water becomes. So as hydrogen ions increase, our pH decreases because this is a logarithmic scale. So that's a little bit confusing, but remember, you just need to remember that as hydrogen ions increase, our pH decreases. We can also look at this in terms of bases. So bases, remember, remove free hydrogen ions from the solution. And by doing that, this is kind of a roundabout way, but in doing that, they actually release, if I could spell, they release hydroxide ions, or those OH ions. So remember, if we're looking at this same solution, we've got all those hydrogen ions floating around in there that were put in there from HCl. Now we're going to add sodium hydroxide, which is our base. So remember, we've got our hydrogen ions from our HCl. We're adding those hydroxide ions, and what do we get? What does H plus OH minus give us? It gives us H2O. So we convert all of those hydrogen ions that we had over here, get converted to H2O, or water molecules. So now we are removing or decreasing hydrogen ions from the solution, and that is going to increase our pH. So buffers then can function either way. They can function as an acid to release hydrogen ions, or as a base, so let's say release hydrogen ions, or they can function as a base to remove those hydrogen ions from solution. So buffers are actually made up of a weak acid and a weak base, and they absorb or take away these ions from the solution. In doing that, they resist changes in pH. Your blood is a very important, one of the greatest buffers that we know of, and that's what helps resist the changes in pH in your cells. Alright, so last slide, I just want to show you how this works. So for example, we have a buffer at pH 5. So its job is to keep the pH at 5. So if we were to shift the pH to a more acidic pH, so we're going to draw a line down the middle here. So let's look at this side first. Let's look at the left side first. If we were to shift the pH down to a more acidic pH, so pH went down, which means we increased hydrogen ions. So we had a flux of hydrogen ions over here on this side. So our pH went down because we added all these hydrogen ions to the solution. The job of the buffer would be to remove the free hydrogen ions. So in this case, our buffer would be acting like a base. Okay, so in this case, our buffer is acting like a base to remove those free hydrogen ions from solution. It does that by releasing hydroxide ions, and now we have water. We get OH minus, now we have water. OH minus, water. Okay, OH minus, which is now water. Okay. If we look over here on the other side, now we have shifted, we've increased our pH, so now pH has gone up, which means we have removed hydrogen ions from the solution. So now what we need to do is we need our buffer to release hydrogen ions back into the solution to bring that pH back down. So now our buffer is going to be acting like an acid to introduce hydrogen ions to the solution. Remember, when we increase our hydrogen ion concentration, we decrease our pH and bring it back down to 5, where we want to be. All right, that's chapter 3. I'll see you in class.